Why do some sequences of functions behave nicely, while others completely break down? Today, we uncover one of the most powerful results in topology. Our map for this terrain is James R. Munkres's classic text, Topology. In standard analysis, if you have a sequence of continuous functions, you expect their limit to be continuous as well. But in higher-level topology, that assumption fails. To resolve this, mathematicians had to reconsider how we define the distance between two different functions. We will define pointwise convergence and compact convergence, and then prove Ascoli's theorem, which brings order to infinite-dimensional spaces. If we cannot trust the limit of a continuous function, entire fields of modern analysis collapse. Fixing the topology is a mathematical necessity. We start with pointwise convergence. This is the simplest metric, where you calculate the limit at every individual x-coordinate independently. In this diagram, notice the vertical dashed lines, representing individual coordinates. The points slide straight up and down to their local limits, ignoring the overall shape of the function. This concept corresponds to the product topology. Because it treats every point in isolation, it is usually too weak to preserve continuity. We need a stricter condition. Uniform convergence demands that the entire sequence gets close to the limit everywhere at exactly the same time. To visualize this, look at this epsilon tube. It is a shaded band drawn perfectly around our limit function, stretching across the entire domain. For a sequence to converge uniformly, its wavy function lines must eventually stay completely inside this infinite boundary. However, uniform convergence is often too restrictive. The middle ground solution is compact convergence. Watch the epsilon tube shrink. Now it is only covering a restricted, closed interval from A to B, leaving the ends of the function unbounded. Compact convergence is a useful compromise. It relaxes the rigid global bounds while remaining strong enough to preserve continuity in locally compact spaces, like the real number line. Let's test these three definitions against a classic counterexample, a sequence of functions defined by a single shifting bump of height 1. Here's a flat line with a shifting bump. Pointwise convergence succeeds. As it passes a marker, the value drops to 0. Compact convergence also succeeds once the bump exits any highlighted interval. But uniform convergence fails. The bump always protrudes outside a global epsilon tube. This proves that compact convergence captures the eventual 0 behavior that uniform convergence is too rigid to recognize. In finite spaces, the Bolzano-Weierstrass theorem guarantees that bounded sequences have convergent subsequences. But in infinite-dimensional function spaces, this isn't enough. Look at this sequence. These functions are strictly bounded between y equals -1 and 1, but they vibrate into a blur. Points stay bounded, but the functions never settle on a limit. We need a new constraint, equicontinuity. This is a shared limit on how wildly a family of functions is allowed to change. To visualize equicontinuity, consider several distinct curves passing through a single point, x0. For a single function, we draw a delta epsilon box centered here. Equicontinuity ensures this exact box size restricts every curve in the sequence simultaneously, sharing the same local bounds. This leads to Ascoli's theorem. It states that if a family of functions is pointwise bounded and equicontinuity, it is guaranteed to have a uniformly convergent subsequence. Deploying the theorem requires this checklist. The domain X must be compact, the range Y must be a metric space, and the sequence must be both pointwise bounded and equicontinuity. The proof follows a clear logical path. First, we identify a countable dense subset, a set of representative points scattered throughout X. We then use a step-by-step refinement process to extract a specific subsequence that is guaranteed to converge at every one of those representative points. Finally, because equicontinuity limits how much these functions can deviate between those points, the convergence at our scattered markers forces the entire function to settle uniformly. Ascoli's theorem provides the logical bridge needed to convert localized, bounded behavior into guaranteed global convergence across the entire space. Let's consolidate the final takeaway from these different topologies. This matrix shows the hierarchy we've explored. Pointwise convergence is the simplest, but it is often too weak to maintain the function's core properties. Compact convergence is the useful middle ground, ensuring uniform behavior on all compact subsets. And Ascoli's theorem is the critical result that extracts convergence out of bounded, equicontinuous chaos. Understanding these topological upgrades is what separates basic calculus from rigorous functional analysis. If you found this helpful and want clear explanations from standard books like Munkres, don't forget to like the video and subscribe to the channel.